So this is the point where we stopped last Monday, and so the question that I raised was regarding this particular diagram, which is a very simple question. But you need to explain the answer correctly, right? So the writing the answer is important. So I got one answer from one of you. Other than that, nobody had tried it. So make sure that you try the question. The question is also uploaded as an assignment in the LMS, as I told you. So make sure that you go there and check the assignment and answer, give an answer for that. I don't need like 2-page or 3-page answers, right? So just a half a page or even less than that. It doesn't matter. So what is important is you correctly explained what is answered, right? So that's only. So it doesn't matter whether you write three lines or 5 lines or 7 lines, right? As long as the answer is clear and correct, right? Now, this is the last slide, last 2 slides of that particular lecture series about stellar motions. Now, so we have been talking about different types of motions, and there is this nice relation between the mass and the luminosity of a star, right? So I hope all of you know what luminosity means and what mass means when we talk about a star, right? Now there is a relationship between this mass and the luminosity for stars. That is, more massive stars are generally more luminous, right? So when you have higher mass stars, they seems to be more luminous or more bright compared to the lower mass stars, right? Now this relationship has a very famous name called mass luminosity relation, and this graph is actually that. Sorry. So this graph basically shows that particular relationship. In the x-axis, you have the masses, different masses, 0.2, 0.1, 1, 2, 5, 10, 20, like that, solar masses. And then you can see that this is not a linear scale, right? So the scale is, you can see that it's not a linear scale. And then you have the luminosity in the y-axis. And you can see that in general, when mass is increased, the luminosity gets increased, right? So that is the relation. And this relation is roughly, luminosity is approximately equal to 4th power of the mass of the star. Or if you tell it more precisely, we used to tell that it is approximately equal to 4th power 3, not the 4th power, 3.9 power of the mass, right? And this is called mass luminosity relation. And I want you to remember this relation actually, right? So this is one of the important relations we normally used to have, use at different points to compare the luminosities, right? When you know the masses. And also goes into the other opposite direction as well. When you know the luminosity, you can get an idea about the mass of the star. You don't need to remember this one where we used to say 3.9 power to make it easier. So I have put here 4th power of the mass. So it may be easier to use this one, right? But whenever you have to use mass luminosity relation, both of these relations are correct. And if somebody have used this, it is not wrong. It is also correct and also more precise. But however, the calculations will be difficult, right? Because of that, make sure that in an exam, I always expect that you will use this one. Right? But if somebody use this one, it's okay, right? But I mean, it will make things harder because with the calculations, right? Right. So let's see what this relationship means. If you take 2 different stars, which they have masses that are differ by a factor of 2. So that means one star is twice massive compared to the other star. then what happens is this more massive star will be 2 to the power 4 times, so 16 times brighter compared to the less massive star, right? So that is what this particular relation tells you, right? So those are examples. Now, another example is if one star is 1.3 times, 1 over 3 times the mass of the other, then it will be approximately 81 times less luminous compared to the other star, right? So like that, you can use the relationship to estimate the brightness of stars. And also you can go into the opposite direction as well, right? So make sure you remember that relationship, and that is the last slide. And what I want here is just to go through the next set of lectures. This will be, so we will not have a complete class today, but I will go through this series of lectures about exoplanets. So let me share that presentation with you. Right. Now, if anybody else have a question, anyone has a question about the previous, anything from previous presentation about stellar motion and binary stars, I would like to answer those questions. I will just give you a few minutes before I start this one. If anybody needs to ask anything from that presentation, right? Right. So if you do not have any questions, let me start this lesson today about the exoplanets, and I will stop once I am done with this particular lesson. This is a very short one, and at the same time, this is actually the first time that I am. So this is a kind of a new addition to your lectures compared to the last year. So this was actually we didn't talk about exoplanets in last year's lecture. However, now I feel that this may be important for you in future because the field about the exoplanets seems to become like more and more interesting among astronomers and among the research. So there are a lot of research going on this field, and because of that, I have added a basic introduction about exoplanets. Uh, Now, as you know, exoplanets means planets beyond the solar system, right? So there are now astronomers have found large number of planets which are outside our solar system, right? Now, the aim of this lecture, this presentation is to give you a kind of a brief knowledge uh, about this area, and at the same time to explain you uh, basically how we detect exoplanets, right? So what are the methods that astronomers use to detect these planets outside our solar system, and also some of the results, right? So what kind of results we have up to now, right? So that is the aim. So this will just give you a basic idea. Now, as I have mentioned here, the direct observations of planets around other stars are very difficult, and you can imagine that, right? I mean, going beyond the solar system and detecting a star and then look at planets around that particular star will be an extremely difficult one, right? Now, this is why looking for these planets in other solar systems was not popular that much until close to 2000. Now the first exoplanet was discovered in 1995, which was a planet orbiting around the main sequence star, right? So when I tell a main sequence star, I hope that all of you know what that means, right? Because we talked all these things about what is the main sequence and all these things in past lectures. Now, these most exoplanet detections are made using techniques where we observe the effect of the planet X-ray on the host star. So you cannot actually do direct observation. You cannot look at planets outside our solar system directly from a telescope and figure out these planets in other solar systems, right? It is not practical. We don't have, large telescopes or develop technology to go up to that point. So most exoplanets are detected just basically using the gravitational effect. So that means, let's say you have a star and there are planets going around it, right? Normally what happens is not only the planet is going around the star. So what actually happens is there will be a common center of mass between the common center of mass for the planet and the star, right? Now, this system will be going around that particular center of mass, right? And remember, this is like the same two-body problem like situation that we learned in classical mechanics as the second chapter, as far as I remember, and you had a question in the exam as well. Now, so what that means, the gravitational tug of an unseen planet will cause a small wobble in the host star. If its orbit is properly aligned, the planet will periodically cross in front of the star, causing the brightness of the star to dim. So what happens is this is pretty much similar to these eclipsing binaries that we talked last day. So that is when you have a star going around another star, there will be a loss of brightness, right? Now the same thing will happen here. If you have a star and then there is a planet going around it, when the planet goes in front of the star, there will be a dim or the loss of the brightness from the star when you look at from here, right? And at the same time, there is another thing that could happen. This gravitational tug of an unseen planet will cause the small wobble in this host star. So that means if you have a star and a planet, so what happens is, due to this gravitational effect, the star also wobbles a little bit, which means it also moves here and there, right? Now, these are the two properties that astronomers normally use to detect exoplanets, and let's look at the first one and how it is used. Now, this is what I have mentioned. Now, here is a planet right here, unseen planet, and due to this planet, the star will wobbles around like this, right? And because of that, basically what happens is the motion of a star is around the common center of mass, because let's say star is huge and there is a small planet here, and then there will be a center of mass of these two systems close to the star, right? So the star will move around that center of mass, right? Now, this movement is actually very small that you cannot detect it from this, just looking at the motion, right? Because from the amount of movement is so small that it is hard to detect it from a telescope, right? That is the main issue that we have when you detect exoplanets like this. So instead of looking at the change in position of the star with the time, which we called as astrometry in astronomy, we are actually looking at the Doppler shift of the star, right? because the change in position is so small that it is not that much easy for us to detect that. And because of that, what we are looking at is actually Doppler shift of the star, right? As you see from here, it's a simple mechanism, as you know. When there is a star that goes away from you, which means if the star goes away from you to this side, the light that receives to us will be redshifted. And when the star is moving towards us, the light that moves towards us will be blue shifted, right? So this is what happens. Now we can use this particular effect, which we called as the Doppler effect, to detect and decide or conclude that there is an unseen planet around this star, right? So this is one way of detecting exoplanets or planets around other solar systems, which we called as a Doppler method. Right, so I have explained it here. As the star and planet orbit each other, part of their motion will be in our line of sight, and such motion can be measured using the Doppler effect and the star spectrum. And the first successful use of the Doppler effect to find the planet around the star was in 1995, as I showed you. So that people who found this first exoplanet, so they have used this Doppler method, and these two astronomers, Michael Mayer and Dider in Geneva Observatory, used this technique to find a planet orbiting around a star called 51 Pegasi. Right, so this is the first star they found, and this star is around 40 light years away from us. And interestingly, the planet only took 4.2 days to orbit around the star. Right, now this is why it was easy to detect, right? And now actually we have detected around 900 giant planets using this Doppler technique, right? So this is one of the techniques that we are using to detect Doppler exoplanets. And you can now understand why you need physics to learn astronomy, right? So this is one of the questions that sometimes people ask. You can see that these, whatever the things that you learn in physics, such as Doppler method, you have to apply it here in astronomy to detect different things. Right. The other method is actually about transiting planets. So that is very similar to what we have talked about under eclipsing binaries. As you can see here in this diagram, you have a star at the center, and then there is a planet going around that star. And what would happen in terms of the brightness is, when you have, let's say you have this planet at position 1, then you can see that at position 1, the star is not covered by the planet. And because of that, the brightness that you receive from the star will be stable. And at point 2, you can see that the planet partially covers the star. And because of that, there will be a drop in the light at this particular position, right? And after that, when it comes to point 3, like right here, the planet completely goes in front of the star. So you will have the maximum light drop, because the light coming from this region comes from this region of the star will be completely blocked, right? So because of that, you will have a dip like this. So this is another way of detecting exoplanets, and we used to call this as transiting planets, right? Now there are specific names to these 3 positions. The first one is called out of transit, and I have mentioned it here. And the second one is called transit ingress. And the third one is full dropping brightness, right? So those are the 3 positions, right? Once again, this is the second method of detecting exoplanets. And nowadays, these are the two basic methods that we use to detect exoplanets. And we can use to calculate something called transit depth. When you are looking at these transiting planets to discover planets. So what actually happened is, in a transit, the planet's circular disk blocks the light of the star's circular disk, right? So there are, when you look from one side, there is a circular disk of the planet that blocks the circular disk of the star, right? As you know, as area of a circle is pi r squared, and from that we can calculate the amount of light that the planet blocks, and this is called the transit depth, right? Now, these words are very important, right? So because you have to understand the words as well. So in other, in the coming slide, if I call or find a value called transit depth, then you need to understand what that means, right? Other than that, the calculation is very simple. What you need to do to find the transit depth is, you just find the area, circular area of the planet, because you just do it for one plane. Other than, planets are approximately spherical shape, but here you only need the circular area and then the circular area of the star, right? So you divide those two, and basically, 5 cancels out, and basically it will be radius squared of the planet and radius squared of the star, right? And then you have to find this value right here. And this value is what we called as the transit depth, right, for transiting planets. So make sure that you understand it, and if you have to calculate it at some point, and this is how you do it. And there is an example here. So that is just about our own sun and the Jupiter, and you just get the radius of the Jupiter divided by the radius of the sun. And this transit depth came as 0.01, or you can write the same thing as 1% transit depth, right? So both are correct. Right, so those are the two, main methods that we use to detect these exoplanets or planets around other stars. Now, so there are different things that you can calculate from these two different methods. Now, when you use this Doppler method, you can calculate or estimate the mass of the planet. And you may be wondering how you can do it. That's because you can find the speed. And if you think about this in terms of the Kepler's laws that you have learned, t squared equal r to the power 3. So there is a way that you can calculate the mass, right? Mass of the planet. And if you can study the same object from transit techniques, so that is the second technique that we have used. So that means we can measure both the mass and the size of the exoplanet, right? Because from the transit technique, you can get the size, right? And from the Doppler method, you can get the mass, right? So advantage is that if you can use both method to look at one particular planet, which means you can find the mass and the size of the planet, and that will give you average density of that particular planet, right? So that is the advantage. And in 1999, from ground-based telescopes, this first transiting planet was detected, right, which is an orbiting star around a star called HD 209458. So that is just a catalog number given to a star, and this is actually measured from both methods. And this was the first case where we could determine what an exoplanet was made of, right, with that mass and radius. And this particular planet was actually a gas and liquid world. which is very similar to our Jupiter and Saturn. Right, so this is just for your information, and it is, I guess, important that you know about these things. And this is the Kepler spacecraft, and this is named under Kepler's name. And I think I have mentioned this even in very earlier lectures as well. And this main name of this particular spacecraft is to detect exoplanets. Right, so it is looking at actually this particular region of the sky, and to detect these exoplanets, you have to look at for a long time in for the same locations, because some of these planets have large periods, right? So you have to look for years. Now, anything, as far as I remember, anything under 4 years, the Kepler spacecraft is capable of detecting those, right? So the idea is this Kepler spacecraft taking images for over 150,000 stars in this region to find transiting planets. So that is the main method that Kepler's telescope is using. So basically, it tries to detect exoplanets using this transiting method, right? Transiting planets, as we have discussed earlier. And here are the results that we have up to now. So as you can see, all these yellow dots that you see in this diagram. So these are the discoveries made by transit method, right? And most of them are done by this Kepler telescope. And if I name this axis, the x-axis is the orbital period of these exoplanets, and the y-axis is the radius of a planet, right? So those are the two axes, and there are different colors that I have here. And if you read through this particular caption right here, the yellow and red dots show planets discovered by transit methods, right? And the blue dots are the discoveries by the radial velocity or the Doppler technique. So these blue color ones are the planets that are discovered from the Doppler technique, and these yellow colored one are the planets that are discovered from transit methods. And this is actually a nice graph that you can clearly see that when you use the Doppler method, you can you have most of the time statistically you have detected planets that have larger orbital periods, and also in terms of the size, they are large in size, right? So most of them fall into this area, right? And you can probably understand that the Doppler technique is kind of a more biased method in that sense, right? So it can only detect these planets which are larger in size, right? So that's because of the sensitivities that we can obtain even from the Doppler techniques when you have the large sizes, so they are easy to detect. And you should understand why is that, right? Because the size is larger, which means their radial velocity should be larger, and measurement size here, right? So that's the reason. And when you have a smaller planets, radial velocities are smaller, so that it's hard to even detect those using this Doppler method, right? So these are the things that you have to think analytically and decide actually what has happened here, right? So these are the things that most of the time you used to come across when you do research, especially for the postgraduate studies. You look at graphs and look at the data, and you have to understand those, why that happens and why these things happens like that. And these type of things are called actually, as far as I remember, selection effects. So which means the data is biased, right? So it's not fair to conclude something, when you have, a sample like that, you can clearly see that that particular method has only worked for larger size planets. Right? But for the transit planets, you can also detect these smaller planets as well. So this graph actually tells you a lot of things. So that's why I have a graph here. And here are some of the key discoveries made by the Kepler. So this graph shows the planets discovered by the Kepler. So if I read this, the bar graph shows the number of planets of each size range found among the first 2,213 Kepler planet discoveries. So these are 2,213 planets discovered by this Kepler telescope, and the size ranges from half the size of Earth to 20 times that of the Earth. And just try to understand the graph, and you can probably will see an interesting thing that most of the planets that are detected by Kepler in this region, they have detected large number of planets which are around the size of 1.4 times the Earth, up to 2.8 times the Earth mass, when you consider these two bars. And interestingly, these size of planets does not exist in our solar system. Here are the planets in our solar system, right? And you can clearly see that this particular area, you can't see anything in our solar system, which is kind of interesting. And these type of planets, which are larger than the Earth's planets, or the planets like under these two bars, we call it as super Earths because they are larger than Earth, right? And the size distributions are here. You can just go to that as well, which is again interesting. So one of the interesting discoveries is that the most common types of planets in the galaxy are completely absent from our solar system, right? Or were unknown until the Kepler survey, right? And there are approximately 100 billion stars of the spectral types F, G, and K in our galaxy. And if I remind about this, remember that we have learned something called spectral classification, right? You can classify the stars into different spectral types, starting from O, right? O, B, A, like that. And O type stars are the hottest one. And in terms of the main sequence stars, O type stars are the most massive stars, like that you categorize into different regions. And our sun belongs to this type G, as far as I remember. And so around that you get this middle spectral types F, G, and K. There are around 100 billion stars, right? Around that particular that belongs to these three spectral types, right? So our estimate is that there are about 30 billion Earth-sized planets in our galaxy, right? So this comes from this particular diagram right here. So this has average number of planets per star in each planet size range, right? And this distribution is corrected for biases in the Kepler data shows that the Earth-sized planets may actually be the most common type of exoplanets, right? And you can see that approximately 30% of the planets may be Earth-sized planets right here, and that gives you this 30 billion, right? So you have 100 billion stars of these three spectral types, F, G, and K in our galaxy. And because of that, if you look at this graph, you get around like 30% of the planets are Earth size. And that means around 30 billion, we should have Earth-sized planets in our galaxy. This is actually extrapolating the data that we have, right? So that means you try to observe a large sample and then you apply that to the whole galaxy, right? And the reason that we look at F, G, and K type in our galaxy, you have to, I guess you will understand it, right? Because these are the spectral types which are in the middle part of this HR diagram and also close to two sides of our own sun, right? So they have enough time to form planets around the stars, right? So because of that, we believe that F, G, and K spectral types are more, more or less more. They are the stars that are more probable to have, the planets around. We should be able to detect those, right? And if you consider super, so that means these other two graphs, 1.4 and 2.83, you can see that they are the mostly available planets. You will get around 100 billion in the whole galaxy. So that means there will be 100 billion stars. So for each star, we can estimate that there will be one Earth or super Earth in each solar, for each star, right? So that is the estimate, right? Now, as we have discussed before, we can also look at the densities of the planets, right? So there are several hundred planets that we have been able to measure the both size and the mass from those two methods, transit data and the Doppler data. So which means if you can measure the mass and the size, you can estimate the density, right? Now, a key observation so far is that the planets that are more than 10 times the mass of the Earth have substantial gaseous envelope, and lower mass planets are rocky in nature, like our terrestrial planets, right? So this graph right here explains that whole thing. You can see that these lines are actually theoretical lines, how the planets looks like if they have hydrogen, so it goes like that. And if this x-axis is the mass of a planet in terms of Earth masses, and the y-axis is the radius of the planet in terms of Earth radius. And each of these blue lines represent these are like theoretical curves. Where should be a planet if it has only hydrogen, like that, right? There should be a planet if it has only water, and where should be a planet if it has only rock or only iron. And you can see that when the mass increases, with the increasing mass, there are different curves, and then for the hydrogen curve right here, even when you go for higher mass, it goes down as well, right? And you can see that most of these the planets that we have detected is around this region. So that's why we used to tell that these large stars or large planets, they have a gaseous environment which is very similar to our Jupiter and Saturn, because they fall into this very close to this gas curve, right? Hydrogen curve. And when you go into these smaller planets, so they are kind of around these the lines for the rock, iron, and maybe some of them close to water. And there are some green triangles that you can see here. So these are actually the planets in our solar system, right? Different planets in our solar system. Just look at these graphs actually very carefully. The reason that you have a graph here, it has a lot of information. And I always expect from you that you have to understand these graphs and extract the information that this kind of graphs gives you, right? So this is one of the skills that you need to build up for your future studies, right? This always helps for anyone. And as in astronomy, there are always graphs involved in most of these observations, right? Because they are based on data that we have, right? Now, this is a very, very brief introduction about planet systems. And as you know, our solar system has large number of planets, right? So we don't just expect there will be one planet in one solar system. So it comes as a system of planets. And here is the Kepler 62 system, one of the system of planets detected by Kepler telescope, and you can see that there is a habitable zone that you can have from this green color, and this is our solar system compared with Kepler 62 system, right? So I am not going to go into details here because that will, I just need to give you a brief introduction about these things, right? And the next question is, it is true that we have planets, whether we will have habitable planets. So which means whether there are planets that we could one day go and live there, right? Now, while thousands of exoplanets have been discovered in the past 2 decades, every observational technique has fallen short of finding more than a few candidates that resembles Earth. So we have just few candidates which are very similar to Earth, right? Now, the problem is actually astronomers are not sure exactly what properties would define another Earth, right? So we don't actually know what kind of properties that we should have define another Earth, and how habitable a planet depends on both its distance from its star and the nature of its atmosphere. Now you know that our planet Earth is the third planet in our solar system. So we have, a nicely balanced weather and everything that is very suitable for habitable life. And so that same thing may be needed in other solar systems as well. The search for potentially habitable world is one of the prime drivers for exoplanet research in the next decade. So this will be the future research, search for these habitable worlds in one of the main research that will that we have to do in the next decade, right, to find the planet that we can live, right? So this is just the painting that's done by NASA, just to convey the idea that there will be many planets which are similar to Earth out there. And so we have to increase our methods to find them, increase our techniques to find them. So that's the only thing that we can do. But just get a brief understanding about these, the topic about the exoplanets, right? Right, for now. So I'm going to stop today from here just within an hour because there are only, few of you are here. And if all of you cannot actually participate, then just please let me know, then we can actually reschedule it. It's not a huge problem, right? So just tell others that because 2 of them have informed me, and I can see that only half of the class is only here, so I will not do the class next time.